Imagine a world in which the word forest has no meaning yet. There's no familiar green wall on the horizon, no endless ceiling of leaves, no soft carpet of fallen foliage, and no tall trunks standing quietly beside a road or a river. The continents are not empty, but their vegetation is still close to the ground, scattered across damp sediments and shallow wetlands, occupying a landscape that feels open beneath a vast, ancient sky. Then, very slowly, something begins to change. Plants begin to rise. Stems become stronger. Water begins moving farther through their bodies. Roots begin reaching into the ground. Branches begin spreading into the air. A few plants become tall enough to cast shadows over their neighbors. And eventually, without a single dramatic moment announcing it, Earth acquires something it had never possessed before: forests. Tonight, we are going back to that quiet beginning, more than 380 million years into the past, to a time when the first tree-like plants were still experiments in evolution, and the land itself was being transformed by their growth. This is not simply a story about what the first trees looked like. It is the story of how a planet of mostly open land learned how to grow vertically, how roots began to reshape soil and rivers, how ancient forests created new habitats, and how biological innovation became part of the geological history of Earth. So let the modern world gradually fade away. Let the familiar forests disappear from your imagination, and picture instead a Devonian landscape beneath a sky that has not seen a human being, a bird, a flowering plant, or a mammal. Somewhere beyond the horizon, an ancient river is moving slowly across a broad floodplain. Low plants cling to damp ground. Strange arthropods move among stems. And in the distance, a few of the earliest trees are beginning to rise above the land. To understand the first forests, we have to begin before there were trees, because the tree was not a single invention. It was the result of many smaller inventions that accumulated over an immense span of time. The earliest land plants were modest organisms compared with the forests that would eventually cover continents. Plants had already begun living on land by the Ordovician and Silurian, but their bodies were generally small, and their relationship with water was still very different from that of modern trees. Living on land created an enormous physical challenge. In water, a plant is surrounded by moisture and partially supported by buoyancy. On land, it has to support its own body against gravity, prevent itself from drying out, move water internally, exchange gases with the atmosphere, and reproduce in an environment where water is no longer guaranteed to surround every cell. The evolution of vascular tissues was one of the crucial steps in solving these problems. Specialized tissues allowed plants to transport water and minerals upward and distribute the products of photosynthesis through the body. Once internal transport became more effective, plants were no longer restricted to remaining extremely close to the ground. Height became possible, and with height came a new evolutionary opportunity: access to sunlight above competing vegetation. But height also came with a cost. A taller plant needed stronger support, better anchoring, more efficient transport, and a way to withstand wind and gravity. The first forests emerged because evolution gradually assembled enough of these solutions for some plants to become genuinely tree-like. The Devonian period, lasting from roughly 419 to 359 million years ago, was a remarkable chapter in the history of terrestrial life. It is sometimes called the Age of Fishes because of the extraordinary diversification happening in the oceans. But on land, another revolution was quietly underway. Plants were becoming larger, more diverse, and more structurally complex. The first tree-sized forms appeared during the Middle Devonian, and by the Late Devonian, forests had become much more established. These early forests did not resemble modern forests in every respect. There were no flowering plants, no grasses, no familiar broadleaf woodland, and no birds singing in the canopy. Many of the plants belonged to extinct groups whose closest living relatives are much smaller. Yet, the basic ecological architecture was beginning to appear. There were vertical stems, branching crowns, underground structures, shaded spaces, fallen plant material, and organisms taking advantage of the new habitats created by tall vegetation. This is an important distinction because the word forest describes an ecological condition rather than a particular kind of tree. A forest exists when tree-sized plants become sufficiently abundant to create a persistent three-dimensional habitat and to influence the environment around them. By that measure, the Devonian forests were real forests, even though almost every individual plant within them would look strange to modern eyes. One of the most fascinating examples comes from the fossil record at Gilboa, in what is now New York State. The fossil forest there has been studied for more than a century, and the preserved stumps were once mysterious because scientists could see the bases of the trees without knowing exactly what the complete plants looked like. Later discoveries connected those trunks with crowns belonging to a cladixolipsid called Wadieza. The resulting reconstruction revealed a tree-like plant that could reach at least about 8 meters in height, with a trunk and a crown built in a way very different from modern trees. Its architecture was more like a giant tree fern than an oak or conifer, although it was not simply a giant version of any modern tree fern. It belonged to an extinct lineage and used an unusual structural strategy. The trunk contained distinctive vascular strands. The crown consisted of branching structures, and the base had anchoring roots. It is difficult to imagine how alien such a plant would have looked when standing among the first forests. Its silhouette would have been tall and elegant, but unfamiliar, with a relatively narrow trunk rising into a crown of repeated branches. Yet this strange organism had already crossed one of the most important thresholds in terrestrial evolution. It had become tall enough to occupy the vertical world above the ground. The Gilboa forest also teaches us something even more important than the appearance of Wadieza. first forests were not necessarily dominated by a single kind of tree. Later work at the site revealed evidence for a surprisingly complex community containing different kinds of tree-like plants. Some had relatively simple rooting systems, while other plants had different architectures and occupied different positions within the landscape. This means that the earliest forest ecosystems were already communities rather than collections of identical trees. They contained variation in height, structure, rooting, and ecological strategy. The forest was becoming a place where different evolutionary solutions could coexist. Some plants could specialize in wetter areas. Others could occupy better drained ground. Some could rise above their neighbors, while others could survive beneath taller vegetation. Even at this early stage, the forest was creating environmental gradients. Sunlight was stronger above the canopy than below it. Moisture could be retained beneath vegetation. Soil conditions differed around roots and fallen plant material. River margins differed from elevated surfaces. A landscape that had once been relatively simple was becoming a patchwork of habitats. The most important part of the first tree may not have been above the ground at all. It may have been the root. Before deep and extensive root systems evolved, plants were more limited in how far they could move into the interior of continents. Roots provided anchorage, access to water and minerals, and a way to interact directly with the physical material of the land. When roots penetrated sediment, they did not merely occupy it. They disturbed it, stabilized some areas, created channels, altered chemical conditions, and contributed organic matter. Roots also interacted with microorganisms and fungi, turning the ground beneath a forest into a biologically active environment. This underground transformation was enormous because it connected the living world to geological processes. A plant could now influence the weathering of rocks, the movement of water, the stability of riverbanks, and the transport of sediment. The development of roots therefore helped turn vegetation from something that simply lived on the landscape into something that could actively reshape the landscape. Imagine standing beside a Devonian river before extensive forests had developed. The river would move across broad areas of sand and sediment, and its channels could shift more easily because there were fewer deep root systems holding the banks together. Now imagine the same river after tree-sized plants become established along its margins. Their roots penetrate the ground. Their stems interrupt water flow. Fallen branches collect sediment. Organic material accumulates. The river still floods and changes course, but its interaction with the land is different. Modern studies of river systems help scientists understand this principle. Vegetation can stabilize banks, influence channel geometry, and change how sediment is transported. The Paleozoic fossil record shows that the evolution of vascular plants, and especially rooted vegetation, coincided with major changes in river styles. This does not mean that the first trees instantly transformed every river to a modern meandering channel, because ancient environments were far more varied. But it does mean that the rise of plants changed the physical behavior of continental landscapes. A tree growing beside a river was therefore doing more than surviving beside water. It was participating in the evolution of the river itself. The same roots that helped stabilize sediment also changed the chemistry of the ground. Weathering is one of the great geological processes that continually breaks down rocks and minerals. Water moving through soil can react with minerals, dissolve certain components, and carry them toward rivers and oceans. Roots can increase the contact between minerals and water, physically fracture substrates, and create chemical environments that differ from those of bare rock. Microorganisms and fungi add another layer of complexity. As plants and their associated organisms became more abundant on land, the weathering system became increasingly biological. The surface of the continents was no longer simply rock exposed to rain and wind. It was becoming a living interface. This is one reason the emergence of forests is so important to Earth history. The first forests did not just add green color to the continents. They changed the way continents interacted with water, minerals, sediments, and the atmosphere. There is a temptation to imagine that the first trees immediately caused a dramatic global climate transformation. But the real scientific picture is more subtle. The carbon cycle of Earth is controlled by many interacting processes, including volcanic outgassing, ocean chemistry, rock weathering, organic carbon burial, and biological activity. Forests became an important new component of this system, but they were not acting alone. Recent research has even challenged older ideas that the rise of forests by itself caused an enormous collapse in atmospheric carbon dioxide. Some evidence suggests that major changes in atmospheric chemistry and weathering were already underway before forests became widespread, driven by earlier vascular vegetation and other processes. What we can say with confidence is that the expansion of plants on land created new pathways for carbon and nutrients to move through the Earth system. Trees stored carbon in their bodies, roots connected organic matter to soil, and buried plant material could eventually become part of the geological record. The forest became another participant in the long conversation between life, rocks, oceans, and atmosphere. The first forests also changed the meaning of sunlight. Before tall plants became common, most terrestrial photosynthesis happened close to the surface. Once trees rose above the ground, sunlight became vertically divided. The upper parts of the forest could receive intense light, while the ground below became increasingly shaded. This created a new ecological problem and a new ecological opportunity. Plants could compete for height, but plants that tolerated shade could also occupy the lower layers. The forest became a three-dimensional competition for energy. A tree did not merely need to grow, it needed to decide, through its inherited architecture, where to place its photosynthetic surfaces. Some ancient trees had crowns made from from repeated branching structures rather than the broad leaves of modern trees. Others, especially later Devonian forms such as Archaeopteris, had leafy branches and a much more recognizable tree-like architecture. The important point is that the first forest was already beginning to divide the landscape into different light environments, creating niches that had never existed before. This vertical structure also created new habitats for animals. Land arthropods were already present before forests became widespread, but a tree added surfaces, shelters, and food sources that simply did not exist on open ground. An arthropod could move along a trunk, hide beneath bark-like tissues, shelter among roots, or explore fallen branches. Decomposing plant material could support communities of small organisms. The forest floor could retain moisture more effectively than exposed ground. The canopy could provide elevated surfaces. We should not imagine a Devonian forest filled with the familiar sounds of birds, mammals, and modern insects, because none of those groups existed in their modern forms. Instead, the forest was inhabited by a much quieter and stranger community of arthropods and microorganisms. The absence of flowers is especially important. There were no flowering plants, and therefore no modern flower-pollinator relationship. The reproductive landscape was dominated by spores, and increasingly by the early evolution of seeds in some plant lineages. The forest was a world before flowers, before fruits, and before the familiar colors of modern woodland. The ground beneath the forest would have been equally unfamiliar. There would be no grass forming a continuous carpet, and no thick layer of modern leaf litter produced by flowering trees. Instead, the ground would have contained plant fragments, roots, organic material, mineral sediments, and the remains of organisms adapted to an ancient ecosystem. Fallen branches could become shelters and surfaces for decomposition. Dead roots could create channels. Organic material could accumulate in wet places. Microorganisms and fungi would break down what they could, returning nutrients to the system. The first forests therefore created not only a canopy, but a new kind of forest floor. Death became part of the architecture. When a tree fell, it did not simply disappear. It could alter light conditions, block water, trap sediment, provide habitat, and eventually become part of the soil. The forest was beginning to recycle its own structure. As these processes accumulated, the forest became a system capable of changing itself. A living tree created shade. Shade influenced the plants beneath it. The plants beneath it contributed to the organic layer. The organic layer changed the soil. The soil influenced roots. Roots influenced water and sediment. Water and sediment influenced where new plants could establish. When a tree died, a gap opened and sunlight returned to the ground. New plants could colonize the opening. This cycle of growth, death, disturbance, and replacement is familiar to modern ecologists, but its beginnings stretch deep into the Paleozoic. The first forests were not static stands of trees. frozen in perfect order. They were dynamic ecosystems, responding to floods, storms, changing water levels, competition, disturbance, and the life cycles of their plants. And then there was the astonishing diversity of tree shapes. Evolution did not produce one universal tree design. Tree-like architecture evolved independently in several plant lineages, including lycopsids, sphenopsids, ferns, and progymnosperms over the course of the Devonian and later Paleozoic. Some plants achieved height with structures that resemble modern trees only superficially. Others developed woody tissues and extensive branching systems. Some reproduced by spores. Others eventually developed seeds. This repeated evolution tells us something profound about natural selection. A tree is not a single evolutionary invention belonging to one family. It is a recurring solution to the problem of competing for light while remaining anchored to the ground. When conditions make height advantageous, evolution can discover the same broad strategy more than once, even if the internal anatomy and reproductive biology are completely different. Among these different experiments, Archaeopteryx became especially important. It was a progymnosperm, an extinct group closely related in evolutionary terms to the lineage leading toward seed plants. Unlike the cladoxylipsid trees of the earlier Middle Devonian, Archaeopteryx had a much more modern-looking combination of features. It developed substantial wood, large branching systems, leafy twigs, and extensive roots. It could reach around 10 meters or more in height, and its architecture suggests a plant capable of building a substantial, persistent canopy. Yet it still reproduced with spores rather than seeds. In that sense, Archaeopteryx represents a remarkable evolutionary bridge. It had some of the structural characteristics that would become familiar in later seed plant trees while retaining an older reproductive strategy. It shows that the modern tree was assembled piece by piece. Wood could evolve before seeds became dominant. Deep roots could evolve before flowering plants existed. A modern-looking crown could appear in a lineage that was not itself a modern tree. The roots of Archaeopteryx are particularly important because they reveal how far the underground revolution had progressed. Fossil root systems from late Devonian sites show extensive structures spreading through ancient soils, giving the trees greater access to water and nutrients, and providing stronger anchorage. This allowed them to grow in environments that were not simply the wet margins of shallow water. Archaeopteryx became capable of occupying seasonally wet and better drained landscapes, helping forests spread beyond the narrowest habitats. This expansion was one of the great changes in the history of terrestrial ecosystems. Once plants could establish deeper roots and survive farther from permanent water, the interior of continents became increasingly available to vegetation. The land was no longer just a collection of isolated wet patches. It could support connected plant communities across broader floodplains and uplands. The forest therefore expanded in two directions at once. Above ground, plants climbed higher and created more vertical habitat. Below ground, roots reached deeper and created more extensive connections with the substrate. The tree became a bridge between sky and soil. Leaves captured sunlight and exchanged gases with the atmosphere. Stems transported water and nutrients. Roots interacted with minerals, water, fungi, and microorganisms. A single tree connected several Earth systems through its living body. When many trees did this together, their combined influence became enormous. Forests could alter runoff, sediment movement, soil development, nutrient cycling, carbon storage, and local climate conditions. They were not passive communities. They were active participants in the transformation of the continents. There is something deeply strange about realizing that all of this began before the modern concept of a forest had ever existed. There were no humans to see the first canopy. There was no language to describe it. No one stood beside the first tree and understood that a new kind of ecosystem was being created. The plants simply grew. Generation after generation, they solved local problems. A stem that supported itself a little better survived. A root that reached water more effectively helped its plant reproduce. A branching pattern that captured more light became part of the next generation. There was no plan, only variation and selection operating across enormous spans of time. Yet, the result was a transformation that would eventually reach far beyond the plants themselves. The first forests also changed how rivers carried sediment. Modern research into Paleozoic landscapes shows a broad relationship between increasing vegetation and the diversification of river systems. In landscapes with little vegetation, channels could migrate rapidly and broad sheets of sand could dominate. As rooted plants became more common, banks could become more stable, muddy floodplains could develop, and woody debris could begin influencing channel structure. The earliest forests were therefore part of a feedback between plants and rivers. Rivers created new surfaces for plants to colonize, while plants changed the stability and geometry of those rivers. This relationship continues today. A forest growing along a river is not merely a decoration beside the water. Its roots, trunks, branches, and organic material can change the movement of sediment and water. The Devonian world was beginning to discover this relationship for the first time. Picture an ancient flood arriving after heavy rain. The river rises and spreads across its floodplain. Water moves around the bases of tree-like plants. Sediment settles in shallow areas. Branches and fallen trunks collect debris. Roots hold portions of the soil together. When the water retreats, a new layer of sediment remains across the landscape. Plants colonize the newly exposed surfaces. Some seedlings or spores establish quickly, while other areas remain open. Over repeated floods, the forest and the river become inseparable parts of the same system. The river determines where moisture and sediment are available, while vegetation changes how that material is retained and redistributed. A landscape that once behaved largely as a physical system becomes increasingly biological. The same process occurred in the soil. A forest floor accumulates organic material, and roots create a network of channels. Fungi and microorganisms process compounds released by living and dead plants. Water moves through the soil and carries dissolved materials. Minerals are weathered. Some nutrients are taken up again by plants. Others are transported away. The soil becomes a reservoir and a filter. It is not merely a place where trees stand. It becomes a living interface, connecting atmosphere, vegetation, groundwater, rock, and rivers. The first forests helped establish this relationship between vegetation and soil at a scale that was previously impossible. They created deeper and more complex terrestrial environments, and those environments provided new opportunities for both plants and animals. The story of the first forest is therefore also a story about time. The changes we have been describing would have been almost invisible from the perspective of a single generation. A root grows a little farther. A trunk becomes slightly taller. A patch of vegetation expands. A river shifts. A tree falls. Another grows. Millions of years later, the accumulated result is a continent with forests. Geological time turns ordinary biological actions into planetary transformation. This is why deep time can feel both impossibly distant and strangely intimate. The same processes we recognize today: growth, death, weathering, water movement, competition, reproduction, and decomposition were already operating hundreds of millions of years ago. What changed was the scale at which they were occurring and the kinds of organisms performing them. The fossils that allow us to see this ancient world are themselves products of extraordinary accidents. A living tree normally decays. Its tissues are consumed by organisms, broken apart by weather, and eventually returned to the environment. For a forest to become preserved, something unusual has to happen. Sediment may bury trunks and roots before they completely decay. Floods may cover a landscape. Volcanic material may entomb vegetation. Water chemistry may allow mineral-rich fluids to replace or fill tissues. Over immense spans of time, the buried material can become rock. Later, erosion removes the layers above and exposes the ancient forest again. What was once an ecosystem becomes a geological archive. The Gilboa fossils are especially remarkable because some tree bases were preserved in life position, allowing scientists to see where the plants stood relative to one another. This makes the site more than a collection of isolated fossils. It provides a glimpse of spatial arrangement. The trees were not all identical, and their positions reveal a community with multiple plant forms. Later work at nearby Cairo in New York State revealed exceptionally extensive root systems of Archaeopteris, giving another view of how forests were organized underground. Together, these sites show that early forests were more complex than the old image of a few primitive trunks standing in a swamp. They contained different plant strategies and different relationships with the soil. The Cairo discoveries are especially useful because the roots can be studied in place. A root system preserved across the ancient soil surface gives scientists clues about how far the tree explored its surroundings, how densely trees grew, and how the forest occupied space below ground. The roots of Archaeopteris were remarkably extensive compared with the simpler rooting systems of some earlier tree-like plants. This suggests a major change in the way plants acquired resources. Instead of relying mainly on a shallow zone close to the stem, the trees could explore a much larger volume of soil. That would have allowed them to access water and nutrients over greater distances, and to anchor larger bodies more effectively. The evolution of roots also created new interactions with fungi. Modern forests depend heavily on mycorrhizal relationships, in which fungal networks associate with roots and help plants acquire nutrients while receiving carbon from the plant. Evidence for ancient plant-fungus interactions extends deep into the Paleozoic, and it is increasingly clear that terrestrial ecosystems were never simply plants growing alone. The first forests were communities of plants, fungi, microorganisms, arthropods, and geological materials interacting continuously. The visible tree was only the surface expression of a much larger system beneath it. When we imagine a Devonian forest, we should therefore picture not only trunks and crowns, but an invisible web of roots, fungal filaments, microbes, water, and minerals beneath our feet. Above ground, another invisible process was taking place. Plants were exchanging gases with the atmosphere. Photosynthesis captured carbon dioxide and converted it into organic molecules, releasing oxygen as a byproduct. Respiration and decomposition returned carbon to the atmosphere and consumed oxygen. The balance between these processes, together with geological burial and other Earth system processes, influenced atmospheric composition over long periods. By the Devonian, terrestrial vegetation had become abundant enough to participate meaningfully in these cycles. Yet again, it is important not to reduce the story to a single cause. Atmospheric oxygenation and carbon dioxide decline were influenced by many processes, and recent models suggest that important changes had begun before forests became widespread. The emergence of forests was one part of a much longer transition in which life and geology increasingly interacted. One of the most beautiful aspects of the first forest story is that it does not require a dramatic catastrophe to become fascinating. There is no single explosion that creates the forest. There is no one creature that suddenly changes everything. Instead, the transformation happens quietly. A plant becomes slightly taller. Another follows. Roots become deeper. Branches become more complex. The ground becomes more stable. The river changes. More organic material accumulates. New organisms appear. The canopy becomes denser. The ecosystem becomes more layered. Over millions of years, these small changes add up to a world that would have been unimaginable to the organisms living before them. And that is perhaps the most relaxing way to understand deep time. Earth does not always change through sudden moments. Sometimes, the largest transformations are slow enough to be almost invisible. The first forest was built through countless small acts of growth. Every root was a small geological event. Every fallen branch was a new piece of habitat. Every new trunk changed the distribution of light. Every layer of organic material altered the ground. Every generation carried forward a slightly different solution to the challenges of life on land. The forest emerged from repetition, persistence, and time. As the Devonian continued, the landscape became increasingly diverse. Forests occupied different environments, from wet lowlands to better drained floodplains. Some plant communities were dominated by tree-like cladixilipsids, while others contained progymnosperms and other vascular plants. There were also smaller plants living beneath and around the larger forms. The forest was no longer a simple stand of one kind of organism. It was becoming an ecosystem with layers, gaps, edges, wetlands, and open spaces. The first forests had crossed the threshold from isolated tree-like plants to landscapes where trees interacted with one another, and with the physical environment on a much larger scale. The plants themselves were still evolving. Some developed more efficient branching. Others expanded their rooting systems. Some produced more complex leaves. Others maintained unusual crown structures. Reproduction was also changing. Seed plants were emerging, and seeds would eventually become one of the most important innovations in terrestrial plant history, because they protected developing embryos and reduced dependence on free water for the reproductive stage. But the first forests did not suddenly become seed forests. Spore-producing plants remained important for a very long time. Evolution rarely replaces one strategy immediately with another. Instead, different strategies coexist, compete, and occupy different environments. The absence of flowers is worth remembering because it changes the visual character of the ancient world. Imagine walking through a forest with no petals, no colorful blossoms, and no fruit hanging from branches. There are no familiar flowering shrubs beneath the canopy. There are no birds carrying seeds. There are no bees moving from flower to flower. The forest's reproductive structures are often smaller, stranger, and less visually familiar. Spores can drift through air or settle on damp surfaces. Seeds begin appearing in some lineages. The ecosystem has a completely different visual language, yet it still has the basic rhythm of a forest: growth, competition, reproduction, death, decomposition, and renewal. The first forests also existed long before the great Carboniferous coal swamps that later became famous for giant lycopsids and enormous quantities of plant material. It is tempting to blend all Paleozoic forests together, but doing so hides the remarkable diversity of their histories. The Devonian forests were earlier experiments. Later Carboniferous forests included giant club moss relatives, tree ferns, horsetail relatives, seed ferns, and other groups. Some of those plants reached heights far beyond many Devonian trees. Their wetlands produced deposits that would eventually become coal. But the Carboniferous world could only develop its enormous forests because the Devonian had already established the basic ecological possibility of large terrestrial vegetation. The first forests, therefore, belong to a chain of transformations. Early land plants colonized the surface. Vascular tissues improved transport. Plants became taller. Roots became deeper. Tree-like forms appeared. Forest communities developed. Rivers and soils changed. New habitats emerged. Later plant groups expanded the possibilities further. Seeds became more important. Forests spread across continents. The land became increasingly structured by vegetation. Every stage prepared conditions for the next. If we could watch the entire process from above, it would not look like a sudden green explosion. It would look like a slow change in texture. Small patches of vegetation would appear across the continents. Some would grow larger. Tree-like forms would begin breaking the horizon. River corridors would become greener. Forest patches would connect. Open ground would remain between them. Over millions of years, the mosaic would become more continuous. The continents would gradually acquire vertical structure. And somewhere inside that enormous transformation, a strange little plant would grow toward the sky, unaware that its body was part of a planetary experiment. Its roots would spread into the ground. Its crown would capture sunlight. Water would rise through its tissues. Carbon would enter its body. Eventually, it would die. Its remains might be buried. Another plant would grow nearby. Another generation would follow. The forest would continue. This is the quiet power of the first trees. They did not need to be perfect. They only needed to work well enough for long enough. Evolution could then build on them. A better root system created opportunities for larger bodies. A larger body created opportunities for more sunlight. More sunlight supported more growth. More growth produced more organic material. More organic material changed the soil. The altered soil influenced future plants. The environment and the organisms became locked in a feedback loop. That feedback is one of the central themes of Earth's history. Life changes the planet, and the changed planet changes life. The first forests are one of the clearest examples. Plants did not merely adapt to soil, they helped create soils. They did not merely grow beside rivers, they changed river behavior. They did not merely respond to atmospheric chemistry. Through photosynthesis and carbon cycling, they became part of the processes that influence it. The forest became both product and producer of its environment. By the late Devonian, Archaeopteryx had become a major component of many forests. Its combination of wood, leafy branches, and extensive roots made it a particularly successful tree form. It could grow in a range of environments and create substantial canopy structure. Its reproduction by spores is a reminder that evolution can combine old and new traits in unexpected ways. A plant can look modern in one part of its biology and ancient in another. The modern tree did not appear as a complete package. It was assembled over time from separate innovations. This is why asking what the first trees looked like is such a powerful question. It reveals that the word tree is hiding an evolutionary story. The first trees did not all look like miniature versions of today's forests. Some looked like giant branching structures. Some resembled tree ferns. Some had unusual trunks and crowns. Some had deep roots, and others had relatively simple anchoring systems. They were experiments, and many of those experiments eventually disappeared. The modern forest is not a direct continuation of one perfect ancient design. It is the surviving result of countless evolutionary branches. The forest itself is also an experiment that has been repeated many times. After the Devonian came new forests. After the Carboniferous came others. The Permian brought different plant communities. The Mesozoic saw the expansion of gymnosperms and later flowering plants. The Cenozoic produced the forests we recognize today. Climate changed. Continents moved. Mountains rose. Oceans opened and closed. Species disappeared and evolved. Yet the forest remained one of the most successful ecological architectures on land. That persistence is remarkable. The individual trees change, but the concept survives. A forest still uses vertical space. It still connects atmosphere and soil. It still captures sunlight. It still stores carbon. It still influences water. It still creates habitats. It still produces dead material that becomes part of the ground. The first forests established the basic pattern, and later evolution repeatedly refined it. Perhaps the most peaceful image to carry from this story is the ancient forest at the end of a Devonian day. The sun is low. The strange crowns of tree-like plants cast long shadows across the ground. A river moves quietly nearby. The air is warm and humid. Small arthropods move through plant debris. Spores drift on the breeze. Beneath the surface, roots explore the soil, while fungal filaments and microorganisms process the hidden world. Nothing knows what the forest will eventually become. Nothing knows that hundreds of millions of years later, people will uncover fossil roots and trunks and try to reconstruct this lost landscape. The forest simply exists, and perhaps that is enough. It grows because sunlight is available. It draws water from the ground. It builds tissues from carbon. It produces new generations. It responds to floods and storms. It competes for space. It dies and becomes part of the soil. Another plant grows where it once stood. The cycle continues. Across millions of years, the forest changes as continents move, climates shift, plants evolve, old tree lineages disappear, and new ones replace them, until the first forest itself becomes part of the fossil record, and the living landscape passes into geological memory. Yet the influence remains. The soil beneath later landscapes contains echoes of ancient biological processes. Sedimentary rocks preserve the traces of roots and trunks. Carbon-bearing deposits preserve the remains of ancient vegetation. The evolution of modern forests carries the legacy of early experiments in height and rooting. Every tree that rises above the ground today participates in an evolutionary story that began when tree-like plants first started reaching toward the Devonian sky. So when you imagine the first forests, do not imagine a primitive version of a modern woodland. Imagine something stranger and more beautiful. A planet experimenting with vertical life. Imagine plants that had no familiar leaves, no flowers, no fruits, and no modern animal companions, yet were already capable of creating shade, soil, habitat, and ecological structure. Imagine roots beginning to penetrate a continent that had previously been dominated by much shallower vegetation. Imagine rivers flowing through landscapes increasingly shaped by living organisms. Imagine a world in which a tree was not ordinary, but revolutionary. The first forests were not the final form of anything. They were beginnings. They were the first large experiments in turning sunlight into structure on land. They were the first great vertical habitats. They were the beginning of forests as planetary forces. They opened the possibility of complex terrestrial ecosystems that would later support reptiles, dinosaurs, mammals, birds, flowering plants, and eventually humans. None of those later worlds existed yet, but the architecture that would eventually support them was beginning to take shape. There is a quiet lesson in that. Large changes can begin with organisms that seem insignificant when viewed alone. A single early tree was not powerful enough to transform a continent, but thousands of generations of trees could. A single root was only a root. Millions of roots could alter soils and rivers. One fallen branch was a piece of dead plant material. Countless fallen branches could change the physical structure of a floodplain. The forest was created by accumulation, and that is how Earth often changes, not all at once, but through countless small actions repeated for a very long time. The first forests were built that way. A stem grew, a root spread, a crown opened toward the light. A plant died, another grew. The river moved, the soil deepened, the landscape changed, and eventually Earth had forests. The first trees were strange, but their basic challenge remains familiar. Every tree alive today must still solve the same fundamental problems. How to stand, how to move water, how to capture sunlight, how to reproduce, and how to survive among competitors. Modern trees have had hundreds of millions of years of evolutionary history to refine these solutions, but the underlying problem is ancient. The first forests were where the experiment began at a scale large enough to change the planet. And perhaps that is the best place to leave them tonight, beneath their ancient sky, surrounded by a landscape that no longer exists. The river continues flowing through the floodplain. The strange trees stand quietly along its banks. Their roots remain hidden beneath the soil. Their crowns move gently in the ancient wind. There are no city lights beyond the horizon. There are no roads, no buildings, no distant sounds of human activity. Only the quiet movement of water, the slow exchange of gases between plants and atmosphere, the hidden activity of roots and microorganisms, and the patient passage of geological time. The first forests did not know they were first. They did not know they were changing Earth. They did not know that their roots would become fossils, their trunks would become stone, or their landscapes would one day be reconstructed by scientists. They simply grew, and in growing, they created a new kind of world, a world with shade, a world with canopy, a world with deep roots, a world with forest floors, a world where life could occupy the land vertically as well as horizontally, a world where plants became geological agents. That world is gone now, but every forest that exists today carries part of its legacy. The first forests are no longer standing beneath the Devonian sky, but their evolutionary descendants still reach upward toward sunlight. Their roots still enter the soil. Their leaves still exchange gases with the atmosphere. Their fallen tissues still return to the ground. Their canopies still create habitats. Their presence still changes rivers and landscapes. The experiment continues. It has simply changed its shape. And as the ancient forest fades into the darkness of deep time, the final image is not one of disappearance, but of continuity. A strange Devonian tree stands beside a slow river. Its crown rises above the low vegetation. Its roots disappear beneath the soil. The last light of the ancient day rests across its branches. Around it, the first forest continues its quiet work. The world is still learning what a forest can become. The first trees have begun. The roots have taken hold. The canopy has appeared, and Earth has become, for the first time, a forested world. There is another way to picture the moment when the first forests appeared. Imagine the continents as a vast architectural project in which life is gradually inventing rooms. For hundreds of millions of years, the land has been mostly a broad surface, with living organisms occupying the thin layer where water, minerals, and sunlight meet. Then plants begin adding walls, columns, ceilings, and underground chambers without ever intending to build anything. A stem becomes a column. Branches become a roof. Roots become foundations and tunnels. Fallen trunks become bridges and shelters. Soil becomes a living floor. The forest is architecture produced by biology. The first trees did not simply grow into an existing ecosystem. They created physical spaces that other organisms could occupy. This is why the appearance of trees had consequences far beyond the plants themselves. Once there was a vertical surface, something could climb it. Once there was shade, something could specialize in it. Once there was dead wood, something could feed on it. Once there was a deep root zone, organisms could inhabit it. The forest created possibilities, and evolution tends to explore possibilities whenever they persist long enough. In this sense, the first forests were not just botanical communities. They were new environments for evolution. The ancient forest would also have been a place of constantly changing light. At the top of a tree, sunlight could be intense, especially under a relatively clear Devonian sky. Lower down, the same sunlight would have been filtered through branching structures. On the forest floor, illumination could vary dramatically from one opening to another. A plant growing in a gap would experience a completely different environment from a plant growing beneath a mature crown. This created a vertical and horizontal mosaic of opportunities. Plants that could grow quickly might exploit openings. Plants that tolerated shade could remain beneath the canopy. Plants with different heights could coexist because they were not competing for exactly the same light. Even in these earliest forests, ecological complexity could emerge simply because plants were occupying different positions in space. The forest was beginning to behave like a layered system, and that layering would become one of the defining characteristics of terrestrial ecosystems. The air inside an ancient forest would also have been different from the air above open ground. Plants continually exchange gases and water with the atmosphere. Leaves and other photosynthetic structures release water vapor. The canopy can slow wind and create sheltered pockets. Moisture can persist longer near the ground. Temperature can become more moderated beneath vegetation than in fully exposed terrain. We cannot reconstruct every detail of the Devonian forest microclimate, and it would be misleading to imagine a perfect modern rainforest transported backward in time. But the fundamental physical effect of vegetation was already present. Plants create local environments around themselves. A tree modifies the conditions experienced by every organism living beneath it. As more trees appear, those local effects overlap and become an ecosystem-scale phenomenon. The forest floor was a place where the consequences of growth became visible after the living plant had disappeared. A branch that fell from the canopy became part of the ground. A root that died remained inside the soil until decomposers processed it or sediment buried it. Reproductive structures accumulated. Organic material mixed with mineral particles. Water moved through this material. Microorganisms consumed what they could. The boundary between living and dead became a continuous cycle. Modern forests depend on this recycling, and the first forests began developing their own versions of it. The amount and composition of ancient litter would have differed from modern forests because the plants were different and efficient decomposers evolved through time. But the fundamental principle was already established. The forest produced the material that eventually became its own soil. This relationship between vegetation and soil may be one of the most important changes in the history of land. Soil is not simply a passive layer covering rock. It is a dynamic environment created by interactions among minerals, water, air, organisms, and organic matter. Plants can accelerate its development by breaking substrates, adding carbon, stabilizing surfaces, and supporting microbial communities. As roots became more complex, the soil became more structured. The first forests, therefore, helped turn the surface of continents into a biologically active skin. The change was gradual, but once it began, it opened the way for increasingly complex terrestrial ecosystems. Later plants could grow in soils modified by earlier vegetation. Later animals could live in habitats shaped by plant roots. Later rivers could flow through floodplains stabilized by vegetation. The first forest became part of the environmental inheritance received by everything that came afterward. The evolution of roots also changed the relationship between plants and rocks. A root can grow through a crack in mineral material, physically widening it as it expands. Water moving around the root can carry dissolved substances. Organic compounds released by roots and microorganisms can influence chemical reactions. Over long periods, these processes contribute to weathering. The rise of land plants therefore linked biology to one of geology's oldest processes. Rocks were no longer weathering only because of rain, temperature changes, wind, and water. Living organisms increasingly participated in the process. The continents became chemically active in new ways. This is one reason the first forests belong in the story of geology as much as in the story of biology. There's also a fascinating relationship between roots and riverbanks. A rooted bank is not mechanically identical to a bare bank. Roots can reinforce sediment, while stems and fallen wood can create roughness that changes the movement of water. The effects depend on plant type, soil, river size, climate, and flood behavior. But the general principle is powerful. Vegetation can alter the shape and persistence of river channels. Paleozoic rivers changed as vegetation became more extensive, and the fossil record preserves evidence of this transformation in changing channel deposits and floodplain structures. The first forests, therefore, became part of the machinery that shaped the continental surface. A river was no longer flowing through a world that was merely physical. It was flowing through a world increasingly engineered by life. The ancient rivers themselves were essential to the forests. They carried water, sediment, and nutrients across the landscape. Floods created new surfaces for colonization. Channels abandoned by the river could become wetlands or stable ground. Sediment deposited on floodplains created new substrates. In this way, rivers constantly generated opportunities for vegetation. The relationship was reciprocal. Rivers shaped where plants could grow, and plants increasingly influenced how rivers moved. The forest and the river became partners in landscape evolution. Sometimes the relationship was destructive. A flood could bury vegetation or uproot trees. But disturbance also created openings for new growth. A forest that never experienced disturbance would not necessarily be a healthier forest. The cycle of disturbance and recovery was part of the ecology from very early in the history of forests. Fire was another force entering the story. Natural wildfire existed before forests because fossil charcoal provides evidence of ancient vegetation burning. But extensive forests provided much more combustible plant material. Lightning could ignite vegetation under suitable conditions. Fire could remove organic matter, open space, and alter nutrient availability. We we should be careful about imagining Devonian forests behaving exactly like modern fire-adapted ecosystems, because the plants and atmospheric conditions were different. But the basic relationship among vegetation, oxygen, dryness, and combustion was already present. As forests expanded, fire became another process capable of reshaping terrestrial communities. A forest could burn, disappear from a patch of land, and then return through new growth. The landscape was never completely static. Volcanoes added another kind of disturbance, and paradoxically, another pathway to preservation. A volcanic eruption could bury vegetation beneath ash or sediment, destroying a living forest while simultaneously protecting its remains from decay. Over geological time, those buried plants could become fossils. Some of the most remarkable windows into ancient ecosystems exist because something catastrophic happened to them. A disaster that ended the life of a forest can become the reason we know that forest ever existed. Deep time often works this way. Destruction and preservation can be the same event when viewed from different distances in time. The first forests also existed on continents arranged very differently from today. The Devonian geography of Earth was not the map we recognize now. Continents were moving, colliding, separating, and changing latitude. Some areas that are now far apart were once connected, while modern coastlines did not exist in their current forms. Climate, therefore, cannot be understood simply by placing a modern forest on a modern map and imagining it in the past. Scientists reconstruct ancient environments using fossils, sedimentary rocks, paleosols, isotope evidence, and plate tectonic models. A fossil tree tells us about a plant, but the rock around it can tell us about the environment in which it grew. Together, these clues reveal a planet that was both familiar and profoundly alien. The ancient sky would also have been different. Atmospheric carbon dioxide, oxygen, methane, and other gases changed through geological time, influenced by volcanic activity, weathering, ocean chemistry, biological productivity, and carbon burial. The Devonian atmosphere was not simply a modern atmosphere with fewer humans. It belonged to a different Earth system. The rise of vegetation was one part of the long process through which biological and geological cycles became increasingly intertwined. Photosynthesis moved carbon from the atmosphere into living tissues. Respiration and decomposition returned much of it. Burial could preserve some. Weathering could consume carbon dioxide through chemical reactions involving rocks and water. Volcanic outgassing could return carbon to the atmosphere. The first forests entered this enormous cycle without controlling it, becoming one component in a planetary system that had already been operating for billions of years. This is also where the story becomes more interesting than a simple claim that trees cooled the earth. Older explanations sometimes emphasize the idea that the rise of forests caused a dramatic decline in atmospheric carbon dioxide and triggered major global cooling. modern work has shown that the evidence is more complicated. Some substantial changes in atmospheric chemistry and weathering appear to have begun before forests became widespread, when smaller vascular plants were already altering the continents. The emergence of deep-rooted trees still mattered, but its global effect must be understood alongside earlier vegetation, volcanic outgassing, ocean processes, and changes in the burial of organic carbon. The scientific story is therefore not weaker because it is complicated. It is stronger because the evidence shows us that Earth systems rarely respond to a single cause. Archaeopteryx provides a particularly useful example of how evolution can combine old and new traits. Its body looked increasingly tree-like, with substantial wood, long-lived branches, leafy twigs, and extensive roots. Yet, its reproduction was based on spores rather than seeds. It therefore occupied an important evolutionary position between earlier free-sporing plants and later seed plant forests. It is sometimes described as one of the earliest trees with a modern architecture, but it is important to remember that it was still an extinct organism belonging to its own lineage. It was not a pine, an oak, or a direct modern tree. It was an evolutionary experiment that happened to solve many of the same structural problems that later trees would solve again. The wood of Archaeopteryx is especially significant because wood is one of the key innovations that allows plants to support substantial height and maintain long-lived bodies. Wood, broadly understood as secondary xylem, provides mechanical support and a pathway for water transport. In Archaeopteryx, the anatomy of the wood shows sophisticated adaptations for supporting perennial branches and a large body. The evolution of such tissues meant that plants could invest in structures that remained functional for years, rather than producing only short-lived stems. The forest could therefore become a more persistent habitat. A tree did not have to rebuild its entire body every season. It could grow gradually, add new branches, expand its crown, and continue occupying the same physical space. The contrast with Wadi Eza is fascinating. The Gilboa tree represents a different solution to becoming tall. Its architecture was economical, emphasizing a persistent vertical trunk and a crown made from repeated branching structures. Archaeopteryx represented a more complex strategy, with long-lived roots and branches growing together, with the trunk and leafy twigs providing a broader photosynthetic surface. These two plants demonstrate that there was no single path to the tree habit. One lineage could build a tall body using a relatively economical structure, while another could invest in a more elaborate branching system. Both could become trees. Both could participate in forests. Evolution was testing multiple designs at the same time. The first forests, therefore, looked less like a uniform woodland and more like a collection of experiments sharing the same landscape. Imagine one part of the floodplain occupied by cladoxylipsid trees, another containing progymnosperms, another dominated by lower vegetation, and wet areas supporting different communities. The forest edge might be open and sunny. The interior might be shaded. Riverbanks could be disturbed by floods. Elevated ground could be drier. Every location offered different opportunities. This ecological patchwork is one reason scientists are cautious when describing a single first forest. There were multiple early forests in different places and at different times, and their compositions were not identical. The term oldest forest is also more complicated than it sounds. Fossil forests are dated using the geological layers in which their remains occur, and new discoveries can change which site holds the oldest known evidence. Gilboa has long been famous for its roughly 385 million year old fossil forest, while nearby Cairo has produced exceptionally old and well-preserved Archaeopteryx root systems. Other Devonian sites around the world preserve different tree-like communities. The scientific record is therefore continually being refined. The important fact is not that one exact location deserves a permanent title. It is that by the Middle and Late Devonian, forests had clearly emerged as a new terrestrial ecosystem. What would it feel like to walk through such a place? The answer has to remain partly imaginative, because no living human has ever experienced a Devonian forest. But the fossil evidence lets us build a careful mental landscape. The air would be warm in many of the environments where these forests grew, though Devonian climates varied greatly by latitude and region. The ground might be damp near rivers and wetlands. Tall tree-like plants would create shade. The trunks would be unfamiliar. The crowns would not look like modern hardwoods. Small arthropods would move through the vegetation. There would be no grass underfoot. There would be no flowering plants. There would be no birdsong. The forest would be quiet in the modern sense, but biologically active in ways we could barely see. The silence would be especially striking. A modern forest contains layers of sound produced by birds, mammals, insects, frogs, wind, leaves, and human disturbance. The Devonian forest lacked many of those familiar voices. Yet silence does not mean emptiness. Tiny organisms would still be moving. Water would still flow. Plants would still exchange gases. Spores would drift. Fungi and microorganisms would work through organic matter. Arthropods would explore the ground and vegetation. The forest would be alive without sounding like the forests we know. If you stood there quietly, the dominant sounds might have been environmental rather than animal. Water, wind, rain, perhaps the movement of vegetation during storms. The absence of flowers would change not only the sound, but the color and rhythm of the forest. There would be no seasonal carpet of petals, no bright fruit, and no familiar flowering canopy. The plant world was still dominated by older evolutionary lineages. Leaves themselves were also different from the broad megaphyll leaves that became widespread later. The evolution of complex leaves was a major step in plant history, and the earliest forests were built partly from structures that would look much simpler to us. This makes the first forest visually distinct from nearly every woodland we know today. It was green in a broad sense, but its greens belonged to unfamiliar bodies and unfamiliar ecosystems. The animals would have been different too. Arthropods were among the earliest successful terrestrial animals, and forests gave them new surfaces and food sources. Some could move through litter. Others could climb stems. Predatory arthropods could hunt among vegetation. Decomposers could process dead plant material. Later in the Devonian, vertebrates were also becoming increasingly important on land and in shallow freshwater environments. The rise of complex vegetation may have provided shelter and ecological opportunities for these animals. Although the relationship between plant expansion and vertebrate terrestrialization is complex, what matters is that the first forests arrived before the terrestrial ecosystems we would recognize as familiar. They helped create the stage on which later terrestrial evolution would unfold. One of the most profound changes was the expansion of habitat volume. Imagine a landscape only a few centimeters thick. Most organisms must live near the surface because there is little structure above it. Now raise plants several meters into the air. Suddenly, there are trunks, branches, crowns, gaps, and shaded zones. The available living space has multiplied without the continents becoming physically larger. This is one of the central reasons forests can support so much biodiversity. They turn two-dimensional ground into three-dimensional habitat. The first trees were therefore not simply increasing plant biomass. They were increasing the amount of usable ecological space. Below the surface, the same expansion occurred in a different direction. A deep root system creates an underground volume of soil that can be explored for water and nutrients. Roots can spread laterally as well as downward, creating networks that connect different parts of the landscape. The first forests therefore expanded habitat both upward and downward. The tree became a vertical bridge connecting atmosphere, canopy, trunk, root zone, and soil. The ecological system gained depth in every direction. This is why the forest can be thought of as a biological interface between Earth systems. The canopy touches the atmosphere. The leaves interact with sunlight and gases. The trunk connects the canopy to the ground. The roots enter the soil. The soil connects to groundwater and rocks. Rivers carry dissolved material away. The ocean receives what the rivers transport. A forest is therefore a place where many planetary cycles meet. The first forests were smaller and simpler than modern forests, but they established the architecture for this kind of interaction. The carbon stored in wood also gave the land a new kind of memory. A living plant holds carbon temporarily. A dead plant can release it through decomposition. But if plant material is buried before complete decay, some of its carbon can remain in sediments for geological periods. Over later eras, enormous quantities of buried plant material became coal. The Carboniferous is famous for this process, but the development of large woody plants during the Devonian was an important step toward the terrestrial accumulation of carbon-rich biomass. The first forests were therefore beginning a relationship between vegetation and geology that would eventually create some of the most economically important rocks on Earth. Coal itself is not simply compressed forest in a simplistic sense. Coal deposits form under particular conditions, especially where plant material accumulates in waterlogged environments and is buried before complete decomposition. Different coal beds preserve different communities and environmental histories. Yet many coal deposits do preserve abundant remains of ancient vegetation. When we burn fossil fuels today, we are releasing carbon that was captured by organisms in ancient ecosystems and then stored by geological processes. The connection between a modern energy system and a Devonian forest is indirect but astonishingly real. The carbon in rocks can be older than the animals that eventually evolved to use those rocks as resources. The first forests also influenced nutrient movement from land to water. As roots and soil systems developed, minerals could be mobilized and transported through rivers. Organic material could enter streams. Nutrients could reach coastal environments. Increased terrestrial weathering and erosion altered the chemistry of rivers and oceans. Some research has explored whether the spread of forests contributed to nutrient delivery and oxygen depletion in marine environments during parts of the late Devonian, potentially interacting with marine extinction events. These hypotheses remain active areas of research and involve many competing factors, but they illustrate how a forest on land can have consequences far beyond the forest itself. The river carries the forest's influence toward the sea. This is another reason the first forest story feels so large. A tree seems local. A forest can become regional. But the effects of a forest can become global because the materials it processes enter planetary cycles. Carbon moves through atmosphere and rocks. Nutrients move through soil and rivers. Water moves between land and ocean. Sediments travel from mountains and floodplains toward seas. A forest is rooted in one place, but its influence can travel. And yet the tree remains an individual organism. It still has to survive. It still competes with neighboring plants. It still needs water and minerals. It still faces storms, disease, herbivory, drought, and physical damage. The first forests were not peaceful in the biological sense. They were competitive environments. A plant that captured more light could grow faster. A plant with deeper roots could access water during dry periods. A plant that reproduced effectively could spread. Evolution was operating within the forest, just as the forest was changing the environment. This creates a feedback loop between competition and landscape engineering. As plants compete for height, forests become taller. As forests become taller, they create more shade. Shade changes competition. As roots compete for water and nutrients, they become more extensive. More extensive roots change soil. Changed soil influences future competition. The environment and the organisms continuously reshape each other. Evolution is not happening on a fixed stage. The organisms are modifying the stage as they evolve. The first forests were therefore an example of what scientists sometimes call ecosystem engineering. The term sounds modern, but the process is ancient. Beavers build dams, corals build reefs, trees build forests. The difference is that trees do not need to construct anything intentionally. Their bodies create the structure. A tree's trunk is a support system for itself, but it becomes a habitat for other organisms. Its roots anchor the tree, but they also stabilize soil. Its leaves capture sunlight, but they also shade the ground. Its fallen branches are dead tissues for the tree, but habitats for other organisms. The same structure can serve multiple ecological functions. That multifunctional nature is one reason forests are so resilient across geological time. When one species disappears, another may occupy the same structural role. A different plant can become tall. A different group can create shade. A different root system can stabilize sediment. Evolution can replace ecological functions even when the original lineage is gone. The forest persists as an architecture while its inhabitants change. This pattern can be seen repeatedly in the fossil record. Devonian forests were followed by Carboniferous forests dominated by very different plants. Later, gymnosperms became important. Flowering plants eventually transformed forests again. In some regions, conifers remain dominant today. In others, flowering trees dominate. Tropical forests, boreal forests, temperate forests, and Mediterranean woodlands all use different plant communities to build variations of the same basic ecological structure. The first forest was the original experiment in this recurring architecture. It proved that plants could create a stable vertical ecosystem on land. Once that possibility existed, evolution could repeatedly reinvent it. This is why the first trees deserve to be remembered, even though none of them survive. Their descendants are not always direct descendants in a simple family tree sense, but the ecological solutions they discovered remain. Roots, wood, height, branching, canopies, and long-lived bodies became central features of terrestrial plant life. The first forests established the physical grammar of the modern woodland, and the grammar is surprisingly simple. Reach upward for light. Reach downward for water. Build structure. Capture carbon. Exchange gases. Reproduce. Die. Return material to the ground. Grow again. Everything else is variation. The first trees varied enormously, but these basic problems were shared. A plant that could solve them became more capable of dominating space. A plant that could build a canopy could influence the plants below it. A plant with roots could influence the soil. A plant with wood could persist. A plant with effective reproduction could spread. The forest emerged from the interaction of these solutions. It is tempting to call this progress, but evolution does not move toward a predetermined idea of progress. The first trees were not primitive because they failed to become modern trees. They They were successful organisms adapted to their own environments. Their lineages later disappeared because environments changed, competitors evolved, and extinction is a normal part of Earth's history. A plant can be extremely successful for millions of years and still vanish completely. That makes their fossils even more precious. They preserve the record of successful worlds that no longer exist. When we study Wadieza or Archaeopteryx, we are not merely looking at failed ancestors. We are looking at organisms that once shaped landscapes. They were important members of ecosystems that covered parts of continents. Their disappearance does not make their existence less significant. The first forests also remind us that Earth has never had one permanent climate or one permanent ecosystem. Forests can thrive in warmth, cold, wet conditions, seasonally dry environments, and many combinations of these depending on the plant communities involved. The Devonian climate varied across latitude and through time. Some early forests grew in wet lowlands, while Archaeopteryx and related plants could occupy better drained habitats. The fossil record, therefore, reveals a world of environmental diversity rather than one universal Devonian climate. This diversity matters when imagining the ancient Earth. There was no single first forest stretching across the entire planet. Instead, there were local forests appearing in different places, composed of different plants, connected by the broader evolutionary trend toward larger terrestrial vegetation. Some were temporary, some persisted, some were buried, some disappeared through erosion. Others became part of later landscapes. The word forest describes the pattern, while the details belong to each place. One of the most beautiful examples of this local complexity is the ancient landscape preserved around what is now New York State. The Gilboa and Cairo sites were separated by only a relatively small distance in modern geography. Yet, they preserve different pieces of the Devonian forest story. Gilboa preserves the bases of tree-like plants and evidence for a mixed community. Cairo preserves spectacular Archaeopteryx root systems. Together, they reveal a landscape in which different plant forms occupied different ecological spaces. The forest was not a uniform wall of trees. It was a community with neighborhoods. Imagine those neighborhoods at the end of a warm day. Along a river margin, one kind of tree-like plant stands in a dense group. Farther inland, a different plant spreads a broader root network. Low vegetation occupies the gaps. A shallow pool reflects the ancient sky. Arthropods move through the litter. A fallen trunk lies across the ground. In the distance, another forest patch rises above the floodplain. Nothing about the scene resembles a modern city, but the organization is surprisingly familiar. There are edges, centers, wet areas, dry areas, openings, and layers. The forest has learned how to create diversity simply by creating structure. And that structure continues to evolve. As the Devonian approaches its end, the terrestrial world is becoming increasingly sophisticated. Trees are widespread. Root systems are extensive. Seeds are becoming more important in some lineages. Different plant groups occupy different habitats. The foundations for the Carboniferous world are being laid. The first forests have done their work. They have demonstrated that large, rooted, vertically structured ecosystems can exist on land. The Carboniferous will take that idea and expand it dramatically. Giant lycopsids will rise above wetlands. Tree ferns will spread. Calamites will form dense stands. Seed plants will diversify. Vast quantities of organic matter will accumulate. Some of those forests will eventually become coal. But the story of giant Carboniferous forests begins earlier, with the Devonian experiments in tree architecture. The first forests were the opening chapter. And perhaps the most remarkable thing about an opening chapter is that it contains possibilities that the writers cannot yet see. Because those early plants could not know that forests would eventually cover enormous portions of the continents, or that later ecosystems would inherit the architecture they were beginning to build. The first trees could not know that forests would eventually cover enormous portions of the continents. They could not know that animals would evolve to live in canopies. They could not know that flowering plants would later transform forest ecosystems. They could not know that humans would eventually depend on forests for food, materials, climate regulation, and countless other things. They only occupied the world that existed around them. But by occupying it, they changed it. That is the quiet theme running through the entire story. Life changes the environment simply by living. The first forests changed the land simply by growing. And once the land changed, the possibilities for life changed with it. This is why the first forests are one of the great turning points in Earth's history. They were not just a new group of plants. They were a new relationship between biology and geology. The living world became capable of building large structures that influenced the physical world around them. The continents became increasingly shaped by organisms. The forest was alive, but it was also geological. Its roots entered rock and sediment. Its leaves interacted with the atmosphere. Its fallen material became part of soils and sediments. Its water moved through rivers. Its carbon entered the wider Earth system, and its death eventually became part of geological history. The first trees had become part of the planet's machinery. And now, as our imagined journey begins to slow, the ancient forest can become quiet again. The sun sinks lower. The strange crowns of Devonian trees darken against the sky. The river reflects the last light. Roots remain hidden beneath the soil. A few arthropods move among fallen plant fragments. Spores settle on damp ground. The air moves gently through the branches. Nothing dramatic happens. The forest simply continues. One plant grows. Another dies. The river moves. The soil changes. Time passes. And because time passes, the forest becomes history. Eventually, the trees are buried. Their trunks become fossils. Their roots become impressions in ancient soil. Sediment covers the landscape. Continents move. Mountains rise. Seas advance and retreat. New forests replace the old ones. the Devonian world disappears. But deep below the later landscape, the first forest remains, not alive, not waiting, simply preserved. A record of the moment when plants first began building worlds above the ground. And when, hundreds of millions of years later, scientists uncover those rocks, the forest returns in another form. A fossil stump becomes a tree, a root becomes a map, a branch becomes a crown, a layer of sediment becomes a floodplain, a collection of fossils becomes a community. The forest is reconstructed from fragments. The science is careful, but the feeling is almost dreamlike. A world that vanished without witnesses becomes visible again. That is what makes paleontology so powerful. It does not merely tell us what lived in the past. It allows us to reconstruct relationships between organisms and environments that no longer exist. The first forests become a story, not only of plants, but of how landscapes were built, how rivers changed, how soils developed, and how life began occupying the continents in increasingly complex ways. And perhaps that is the final answer to our original question. What did the world's first trees look like? They looked strange. Some were tall and tree fern-like. Some had unusual branching systems. Some had relatively simple roots. Others, like Archaeopteryx, had extensive root networks and substantial wood. They did not all look alike because the tree habit evolved more than once. Their crowns were different. Their trunks were different. Their reproductive systems were different. They belonged to lineages that would later disappear. But beneath all those differences was one shared idea. Rise above the ground. Reach for the light. Anchor below. Build a persistent body. Create a habitat. That was the beginning of the forest. And once the forest began, the history of life on land entered a new chapter. The first trees were not the largest trees Earth would ever see. They were not the most diverse. They were not the most efficient. They were not the most familiar. But they were early enough to change the possibilities available to everything that came later. They were pioneers of vertical life. They were architects without plans. They were geological agents without awareness. They were forests before forests had become ordinary. And that is why, even though their branches disappeared hundreds of millions of years ago, their story still reaches into the present. Every modern tree participates in the same ancient struggle between gravity and growth. Every root still explores the ground. Every leaf still captures sunlight. Every forest still creates a layered habitat. Every fallen branch still enters a cycle of decomposition. Every river flowing through a forest still responds to vegetation. Every forest still links atmosphere, soil, water, and life. The first forests began that pattern. They began it slowly. They began it imperfectly. They began it with plants that would look alien to us, but they began it. And Earth has been living with the consequences ever since. So let the ancient landscape remain for a moment longer. Let the modern world stay far away. Let the first trees stand quietly beside the Devonian River. The sky darkens. The water moves. The roots remain beneath the ground. The forest settles into night. There is no city on the horizon. There are no lights. There is no sound of traffic. There is only the slow rhythm of an ancient ecosystem. Growth, water, light, roots, decay, renewal, and time formed the quiet rhythm through which the first forests were built, with each process repeating across generations, until a landscape that had once been mostly open became a complex terrestrial ecosystem. The first forests were built from those simple processes, repeated for millions of years. And in that repetition, Earth changed. The land became deeper. The ecosystems became taller. The rivers became different. The soils became more complex. The atmosphere became more connected to life on land. The continents became increasingly green. The world gained forests, and the experiment that began with a few strange tree-like plants would eventually produce some of the most important ecosystems the planet has ever known. The first forests are gone, but their architecture remains. Their descendants remain. Their fossils remain. Their influence remains. And somewhere in the deep geological memory of Earth, beneath layers of stone and sediment, the first trees are still standing in a world that disappeared long before our own began. They are silent now, but their silence is not emptiness. It is the silence of deep time, the silence of a forest that grew before anyone was there to see it, the silence of roots that changed a continent without knowing it, the silence of a world becoming something new. And that is where we can leave the first forests tonight, beneath their ancient sky, beside their ancient rivers, surrounded by plants that once represented one of evolution's boldest experiments. They reached upward. They rooted downward. They changed the land. And Earth learned how to become a forested world. There is one more layer to the story that becomes visible when we stop looking at the forest as a collection of trees and begin looking at it as a system of flows. Every forest is a place where matter and energy are constantly moving. Sunlight arrives from above. Carbon enters leaves and other photosynthetic tissues. Water rises from the ground. Minerals move through roots and stems. Organic compounds travel through living plants. Dead material falls back to the surface. Microorganisms process it. Water carries dissolved substances into streams. Rivers carry those substances toward lakes and oceans. The forest is therefore never still, even when every trunk appears motionless. The first forests were beginning to create these connected pathways on land at a scale that had never existed before. The movement of water is particularly important. A tree draws water from the soil and transports it through its body toward photosynthetic tissues. Some of that water eventually returns to the atmosphere. In a modern forest, this process can influence humidity, cloud formation, rainfall, and regional climate. The exact effects of Devonian vegetation are difficult to reconstruct, and ancient plants did not necessarily behave like modern forests, but the physical principle is ancient. Plants connect the ground to the atmosphere. They move water upward and release part of it back into the air. Once forests became widespread, the water cycle on land increasingly passed through biological structures. The movement of carbon was equally important. A tree takes carbon dioxide from the atmosphere and turns it into organic matter. Some of that matter becomes leaves, branches, roots, and reproductive structures. Some is consumed by animals. Some is decomposed. Some becomes soil, organic matter. Some can be transported into rivers. A small fraction can eventually be buried deeply enough to remain in geological reservoirs. The first forests expanded the amount of terrestrial biomass, and therefore expanded the number of pathways through which carbon could move. The forest became a temporary storage system, a food source, a soil-building mechanism, and under certain conditions, a contributor to long-term carbon burial. The movement of minerals also changed. Roots can take up nutrients from soil, and plant material can move those nutrients from one part of the ecosystem to another. When tissues die, some nutrients return to the soil. Others can be washed into rivers. This creates cycles that depend on both biology and geology. The first forests were not nutrient-rich modern ecosystems in every respect, but they were beginning to create closed loops that allowed nutrients to be captured, transported, and reused. This increased the efficiency and persistence of terrestrial ecosystems. Plants could grow where previous vegetation had already modified the substrate, creating an ecological inheritance from one generation to the next. The forest also created a new relationship between life and disturbance. A flood might destroy part of a forest, but it could also deposit fresh sediment that later supported new vegetation. A fallen tree might open a gap in the canopy, allowing younger plants to grow. Fire could remove dense vegetation and create a patch of open ground. A change in river position could transform a dry surface into a wetland, or a wetland into a floodplain. Disturbance was not simply destruction. It was one of the mechanisms through which forests renewed themselves. The earliest forests were likely shaped by this same balance between persistence and disruption. This makes the forest a paradox. It is stable enough to create an ecosystem, but dynamic enough to constantly change. The tree stands in one place while the environment around it moves. Water flows, sediment shifts, branches grow and fall, roots extend and decay, organisms arrive and disappear. The forest is therefore a pattern rather than a fixed object. That pattern can persist even while its individual components are constantly replaced. The first forests established this principle at the beginning of terrestrial ecological complexity. The fossil record sometimes captures these moments of change. A buried trunk may show that a flood suddenly covered a living tree. A layer of sediment may contain a concentration of branches. Root casts can reveal that the surface was stable long enough for extensive rooting before burial occurred. Multiple fossil layers can show forests appearing, disappearing, and returning through time. The rocks become a sequence of ecological snapshots. By comparing them, scientists can reconstruct how ancient landscapes responded to climate, river activity, and biological change. The most remarkable fossils are those preserved in life position, when a tree stump remains upright in the sediment. Its orientation tells us that the plant was standing when it was buried, or that the structure remained intact during burial. When several stumps occur together, their spacing can reveal something about forest density. When roots remain attached, they can show how the plant interacted with the soil. These details turn a fossil from an isolated object into evidence of an ecosystem. The first forests become visible not as individual curiosities, but as communities. The Gilboa Forest is famous precisely because of this community-level information. The preserved bases of trees revealed that large tree-like plants were growing together around 385 million years ago. Later discoveries connected the trunks with Wadieza crowns, allowing scientists to reconstruct a plant that could reach at least 8 meters. Subsequent work revealed evidence for multiple plant forms within the same ancient forest. This complexity was unexpected because the oldest forests were once imagined as simpler than modern forests. Instead, the evidence suggests that ecological differentiation was already developing surprisingly early. The Cairo fossil forest adds another dimension. There, exceptionally extensive Archaeopteris root systems were preserved in ancient soils. These roots reveal a plant capable of exploring a large volume of ground, providing both anchorage and access to resources. The contrast between the rooting architecture of Archaeopteris and that of earlier cladoxylipsid trees demonstrates that the evolution of the forest was also an evolution of the underground world. The canopy could become more complex because the roots became more capable. Above ground and below ground evolution were linked. This connection between roots and crowns is easy to overlook. A tree's canopy is visible, but its size depends partly on what happens underground. A larger crown demands more water and nutrients. A taller trunk demands stronger anchorage. A broader photosynthetic surface creates greater demand for transport. Root systems therefore set limits on what a tree can do above ground. The evolution of extensive roots opened possibilities for larger and more productive crowns. In the first forests, the underground revolution supported the visible revolution. The same relationship continues in modern forests. A mature tree may have a root system extending well beyond the footprint of its trunk. Root networks interact with neighboring plants, fungi, microbes, and soil particles. The canopy and root zone are connected through the transport of water and carbon. The first forests did not have modern root anatomy, but the basic architectural relationship was already emerging. The tree above ground and the root system below ground form one integrated organism. This is another reason the word tree can be misleading. A tree is not just the part we see. The visible trunk and crown are only half of the structure. Beneath them is a hidden network that may be equally important to survival. In the Devonian, the evolution of this hidden network was one of the most consequential steps in the expansion of forests. plants could move farther from permanent water, stabilize themselves more effectively, and interact with deeper portions of the landscape. The continent became increasingly accessible to vegetation. Once plants spread farther inland, the distinction between river edge and forest interior became less absolute. Vegetation could occupy areas that experienced seasonal drying. Some trees developed strategies for surviving periods when surface water was less available. Root depth allowed access to moisture stored below. This does not mean that Devonian forests were independent of climate or water, but it does mean that the terrestrial plant world was becoming less constrained to the immediate margins of water bodies. The continents were opening up. This expansion also changed the visual character of the planet. For billions of years, Earth's continents had lacked forests. Even after plants first appeared on land, the vegetation was mostly low. Then, within a relatively short interval in geological terms, trees appeared and spread. The horizon changed. Instead of seeing only low vegetation, an observer could see vertical structures rising above the ground. The land gained a new dimension. This is one of the most important moments in the visual history of Earth. If a camera could have recorded the Devonian world over millions of years, the footage would be almost impossibly slow. A bare patch would remain unchanged for years. A small plant would grow. A taller stem would appear. A forest patch would expand. A flood would erase part of it. Another patch would grow elsewhere. The changes would be too slow for a human observer to notice in real time. But geological time compresses those changes into a visible transformation. What seems insignificant in one generation becomes enormous when repeated for millions of years. This is why the first forest is a perfect subject for a sleep documentary. Its story does not depend on constant explosions or dramatic twists. Its drama is the drama of deep time. A world changes because life keeps growing. The river keeps flowing. Roots keep extending. Sediment keeps moving. Generations keep replacing one another. The transformation is enormous precisely because it is gradual. The pace of the story can be slow, while the implications are immense. The first forests also invite a different way of thinking about extinction. When a Devonian tree lineage disappeared, the forest itself did not necessarily disappear. Another plant could occupy its ecological role. The architecture survived even when the organism did not. This distinction between ecological structure and evolutionary identity is central to understanding Earth's history. Species are temporary. Ecological patterns can be persistent. The forest is one of the great recurring patterns. The same thing happens after major environmental changes. A forest may disappear from a region, but if conditions later become favorable, another forest can develop. The species may be completely different. The architecture may be different. The climate may be different. Yet the same basic relationship between sunlight, water, roots, and vertical growth reappears. The first forests established one of these recurring patterns. They also established the possibility of a forest edge. An edge is where two environments meet, and edges can be biologically rich because they combine different conditions. In an ancient landscape, the boundary between forest and open ground could provide sunlight, shelter, moisture, and new surfaces for colonization. River margins could create another kind of edge. Wetlands created another. The first forests were therefore not only interiors of vegetation, but mosaics of boundaries. These boundaries were important for evolution. Organisms that could tolerate changing conditions could move between habitats. Plants that could colonize disturbed ground could spread after floods. Animals could move between open and shaded areas. The forest was not an isolated island. It was connected to rivers, wetlands, open floodplains, and other ecosystems. The terrestrial world was becoming a network rather than a collection of separate habitats. This network would become increasingly important as vertebrates moved onto land. The first forests predated the fully terrestrial ecosystems of later eras, but they created structure that animals could use. Shaded water margins, dense vegetation, roots, and fallen wood all provided potential shelter and feeding areas. The evolution of land animals cannot be separated completely from the evolution of the land plants around them. Life was transforming the stage, while other forms of life were learning to use it. The relationship between plants and herbivores also began to develop. Even before modern insects and vertebrates evolved the sophisticated feeding relationships seen today, terrestrial animals interacted with plants. Herbivory creates pressure on plants, and plants respond through physical and chemical defenses. The fossil record preserves evidence of ancient plant damage in some periods, showing that plants were not simply growing without being consumed. The forest became a food web. Sunlight entered through photosynthesis, became plant tissue, and then moved into animals and decomposers. The forest therefore created an energy pathway that could support increasingly complex terrestrial communities. The plants were the primary producers, capturing energy from sunlight. Animals could consume plant material or prey on other animals. Decomposers processed dead tissues. Nutrients returned to the soil. The cycle connected the entire community. The first forests were simpler than modern ecosystems, but the basic flow of energy was already recognizable. Another important feature was the increasing persistence of plant bodies. A tree can live for years and continue occupying the same physical space. This persistence allows other organisms to evolve relationships with it. A trunk can become a stable habitat. A root system can remain in the soil. A canopy can provide predictable shade. The longer the structure persists, the more opportunities other organisms have to use it. The evolution of long-lived trees therefore increased ecological stability at local scales, even while forests remained dynamic at larger scales. This stability also influenced decomposition. A large woody body can take longer to break down than a small, soft plant. ancient decomposer communities were different from modern ones, and the evolution of efficient lignin decomposition occurred over a complex history. But the accumulation of woody material created a new ecological problem. How does an ecosystem process so much structure? The answer evolved through interactions among fungi, microbes, arthropods, physical breakdown, burial, and later geological processes. The forest created its own waste management challenge. The solution was not complete recycling. Some material accumulated, some was consumed, some was buried, some was transported by water, some became part of soil, some remained as dead wood. This imperfect recycling is one reason forests can influence long-term carbon storage. A fraction of the carbon captured by plants can escape rapid return to the atmosphere when it becomes buried. Over geological time, that fraction matters. The first forests therefore participated in the creation of long-lived carbon reservoirs, even if they did not immediately produce the enormous coal deposits of later periods. Their wood, roots, litter, and soil organic matter created more opportunities for carbon to be transferred from the atmosphere into the terrestrial system. The exact global effect is still debated, but the mechanism itself is fundamental to Earth system science. The atmosphere was not only changed by carbon. Oxygen also matters. Photosynthesis releases oxygen, while respiration and decomposition consume it. Long-term oxygen accumulation depends heavily on the burial of organic carbon and other redox processes. Geological evidence indicates that atmospheric oxygen was already rising before the first forests appeared, so it would be inaccurate to credit trees with creating an oxygen-rich atmosphere from nothing. Still, the expansion of vegetation added more photosynthetic activity and more organic carbon to the terrestrial environment. Forests became another part of the long oxygen story. Fire provides a visible connection between oxygen and vegetation. When oxygen and dry plant material are present together, combustion becomes possible. Fossil charcoal shows that wildfire has a deep history on land. The first forests provided larger quantities of fuel and more continuous vegetation than earlier landscapes. A lightning strike could therefore create a disturbance capable of reshaping a forest patch. Fire became another agent in the ecological cycle. A burned landscape would look dramatically different from a living forest. The canopy would be broken. The ground would be exposed. Charred plant material would remain. Nutrients would be redistributed. New plants could colonize. Over time, vegetation would return. Fossil charcoal preserves some of these ancient disturbances. A small black fragment in a rock can therefore represent a moment when lightning, oxygen, and vegetation interacted hundreds of millions of years ago. Storms were another source of disturbance. Tall plants are vulnerable to wind because height increases leverage. A storm can break branches or uproot trees. Fallen trunks create gaps. Gaps create sunlight. Sunlight creates opportunities for young plants. The forest, therefore, contains the seeds of its own renewal. even without fire, the fall of one large tree can change the local environment dramatically. The first forests likely experienced storms of different types and intensities depending on their climate and geography. We cannot reconstruct every ancient storm, but sedimentary evidence can preserve flood events and burial surfaces. A forest covered rapidly by sediment can become an exceptional fossil site. The event that killed the plants also freezes a moment in geological time. This is one reason fossil forests feel almost like photographs. They are not photographs, but they can preserve spatial relationships. A trunk can remain upright. Roots can remain attached. Branches can be buried nearby. Sediment can preserve the ancient ground surface. When scientists map these remains, they can reconstruct a three-dimensional ecosystem. The forest becomes visible not because one fossil is perfect, but because many imperfect fossils fit together. The science of reconstructing ancient forests therefore resembles solving a puzzle with missing pieces. A trunk may be preserved without its crown. A branch may be preserved without its roots. A root may belong to a plant whose above-ground body is unknown. Scientists compare anatomy, age, sediment, position, and associated fossils to determine which pieces belong together. New discoveries can change old reconstructions. The story of the first forest is therefore still being written. This uncertainty should not make the story less interesting. It makes the story more honest. We know that trees appeared in the Devonian. We know that Wadi Eza and Archaeopteryx represent important early tree forms. We know that fossil forests existed in places such as Gilboa. We know that extensive roots evolved and that vegetation changed terrestrial landscapes. But there are details we cannot recover perfectly. We cannot hear the ancient forest. We cannot measure its exact humidity. We cannot watch its seasons. We can only reconstruct what the evidence allows. And perhaps the gaps are where imagination can quietly enter, as long as it does not replace evidence. We can imagine the shape of the trees based on fossils. We can imagine the river based on sedimentary structures. We can imagine the forest floor based on preserved organic material and ecological principles. We can imagine the light because we know how canopies work. We can imagine the quiet because we know which major animal groups had not yet evolved. But we should always remember that the real ancient forest was more complicated than any reconstruction we can create. That complexity is part of its beauty. The first forests were not a finished design. They were a beginning. They were a world in which evolution was still discovering what a tree could be. And perhaps that is the most fascinating answer to the question of what the first trees looked like. They looked like experiments. Some were tall and strange. Some were compact. Some had unusual crowns. Some had deep roots. Some had shallow anchoring systems. Some used wood-like tissues. Others relied on different structural arrangements. Their forms were as diverse as the evolutionary paths that produced them. The forest was therefore not born from one perfect tree. It was born from many experiments happening at once. And over time, Some experiments became more successful than others. The world changed. The Devonian ended. The Carboniferous began. New forests rose. Some old lineages disappeared. New lineages expanded. The forest continued.